paper I submitted with indicator queries in there. We're from Kansas. So the technical contribution in this paper, as I see it, is I approach the problem of providing a generic conversion between similar data types. By similar, I mean data types that have a useful amount of constructors with the same name and same fields. And then the other half of the technical work is sort of exposing this generic conversion to the user in a nice interface. So I'm going to start with just a demonstration of this sort of generic conversion in action to motivate why we're doing this. So for the example, I'm going to do lead elaboration on this tiny data type representing the lambda calculus with leads. So I'm going to be using various namespaces, so this is why we're working on module A for this first part. So here's a first stab at a lead elaborator. Nothing tricky going on. The interesting case is for LEDs. We replace them with an application of the lambda. A few things to note. I'm calling this an imprecise elaboration because it's alpha to alpha. As we're going to see, I'd like this to be more precise. So I consider this imprecise because the codomain doesn't enforce the fact that we're removing the lead constructor. I'd like the type system to guarantee that I'm at least that correct. Okay? There might be other bugs, but it's nice to get a little more assurance out of the types. And then I'm using this sort of cutesy style of recursion because I'm going to be showing variance, and I'd like as much of the code to stay the same to demonstrate that the changes I'm making are small. So again, nothing special here. I'm going to improve this function in two ways. I'm going to make it more precise, as I just discussed. But first, I'd like to point out an opportunity to use some existing work from the generic literature. We can use the Compost operator from Bring It Miranda to sort of tidy up this definition. I don't know if I need to sell the benefits of Compost to this crowd, but the general idea is it gets get a more concise definition. It's kind of easy to see at a glance that the only interesting case here is LEDs. Everything else is just structural recursion, which is what Compost sort of abstracts over. And then from a software engineering benefit, we get sort of a decoupling of the definition of this function from the AX or data type. For instance, you could add constructors to a data type representing products and first and second projections. And this function would continue to work as it's written. So these are the sort of benefits we get from something like Compost. So that's the one improvement. The other improvement is to actually use a more precise data type for the codomain. In the paper, I spend a section talking about precise types, or I think I call them exact types in the paper. This is an example of what I consider a more exact type, in that, with respect to the codomain of this lead elaboration, bexpr guarantees that there's no LEDs left. Obviously, this is a simple example, but in general, you can find, you can enforce kind of more interesting things this way. So with that data type, we can rewrite the elaboration function to be precise. In particular, this is the same as sort of the first definition, except I'm using B for the codomain. And so now I'm guaranteed, if this type checks, that there's no LEDs in the result. So the problem here, sort of the problem that I set out to solve, is that this data type no longer, this function no longer has a type that allows me to use Compost. Compost requires alpha to alpha, but this is alpha to beta. Although we know that beta and alpha are very much related, right? One's just sort of a smaller part of the other. So, sort of the technical punchline of the talk is that I can now, after the work in the paper, we can write this function this way. So it's sort of a syntactic shuffle of the modular definition of imprecise elab, but it has the more precise type. That's sort of the punchline of all my work. Throughout these slides, we're just going to be doing singular recursive data types, no mutual recursive data types, and I'm not using any monads or applicative functors, but the work, the paper in my dissertation talks about how to add those back in. So there's three interesting pieces of this definition syntactically. There's this precise case function, this mysterious underscore, and I added h to Compost, so I call my operator hCompost. So with those three changes, we get retain the modularity benefits, but we also get precise type. So I'll explain those throughout the talk. But first, the underscore references this new data type that I generated as part of the boilerplate for connecting your data type to my library. Because I generate a data type like this for each constructor in your original data type. I call these fields types because it just packages up the fields for the constructor, but there's one fields type per constructor of your original data type. The main point of a fields type is that we let the user write a function that works on just one constructor, but it's still total. Right? So I'm sort of separating the constructors from the original data type, but retaining the syntax. That's the nice programming interface I was talking about. So just to sort of convince you that this is the best of both worlds, we get the precise type, and then like the case and the precise case line up. Aside from the underscore, these two line up, and then Compost and hCompost line up. So it's very much a syntactic shuffle of the original definition, but we also get the precise type. So that's sort of the technical merit of the work. In terms of the more broader scope, sort of stepping back, this is not a solution to the expression problem. In my experience, those have been sort of based on two-level types with an explicit fixed point. And that's not what I'm trying to do, right? I'm just trying to get these precise types on these conversions, but being able to use the modular operator like Compost. So it's sort of a question of seeing how far we can get without using a two-level type. With two-level types, you could write that sort of conversion using the modular inject and project, or like the sort of the subfunctor constraints from data types a la carte. But you can do it without two-level types. And generally, I feel two-level types are sort of a little more heavyweight machinery. I'm just focusing on conditional data types. I'm talking about precise types, but all I really did was remove a constructor. But recently, sort of the advent of dependent types showing up in Haskell with GATs and singleton types, there's ways to be much more precise now using indexes and whatnot. But I'm not supporting that yet, at least. That'd be future work. So again, I'm just sort of exploring how far we can get without dual types, without fancy GATs. And once I restrict myself in those two ways, we end up with pretty much exactly what's needed for what's called nanopasses. This is work by Sarkar, Odell, and Gidvig from 2004 and 2005. It's actually Sarkar's thesis as well. And hCompost turns out to be a significant part of the nanopass methodology in Haskell. So I want to briefly talk about that because it's sort of the perfect, that work is the larger sort of software engineering level motivation for why hCompost is useful, why precise types are useful. So I don't expect you to read this, but this is the curriculum from an undergrad class at Indiana back in 2004, I suppose, probably earlier. But it's table 1 from that paper I just mentioned. In 15 weeks, their undergrad students go from a little scheme language down to code in the Spark family, assembly. And the way they do it, they organize it in a Micropast compiler. What a Micropast means is, they sort of conveniently broke it down by sort of pieces of the compiler by week. But each piece of the compiler is also implemented by a number of very small functions that just do sort of the smallest bit of logic as possible, with the idea being that if you make your function so simple, it's hard to get it wrong. So they decompose the compiler into these phases, and then each phase is into a micropass, and those are so simple that it's sort of difficult to get it wrong once you get to the point of implementing it. So they taught the course based on this, but it's Indiana, they're working in Scheme. So they provide this sort of outline, well, you would know actually. They provide this outline in terms of grammars that various parts of the compiler should adhere to, and what the passes should do, and then let the students run wild. So this paper is about adding a framework and scheme to this, where they get to enforce the grammars for the student, and also help them write some of the functions by providing what was basically some generic programming. So these are micropasses, and that's a micropass methodology. What makes their work nanopasses is that for some of the micropasses, they can leave out the boring parts of the definition. Just like we saw that Compost and H-Compost can be used for like vars and apps, all this sort of things that are just structurally recursive, they allow the student to leave those cases out. And they have a thing called a pass expander, which fills them back in. And it turns out that H-Compost seemed to be precisely the pass expander, but in Haskell. So the pass expander in Scheme is sort of trivial because of the syntactic abstraction mechanisms and the latent typing, so they could just build the syntax as they needed it. But I did it in the type system using generic programming foundations. That's sort of the larger perspective on H-Compost that I found. This wasn't the paper because I hadn't realized it yet. So, as I just said, in Sarkar's thesis, which is about the same topic, they say you could do nanopass in a language like ML and Haskell, and there'd be no need to run some checks. So it could be a better fit for the general methodology of enforcing these grammars. But they said it won't work because you don't have macros. So we got to kind of worked around that by using template Haskell for reflection only, and then the type classes and sort of the instant generics methodology, plus the GHC inliner to achieve the generative programming. That would be the other half of the syntactic abstraction mechanism. So nanopath sort of says that this is helpful. This sort of the expressiveness of the H-Compost operator is helpful, but is it helpful outside of Scheme? Is it helpful outside of education? So compiler nanopasses are for compiler education. So here's just a couple examples I found where you see the sorts of things that nanopasses mitigate. You find them in Haskell. So the first is just a paper I was reading the other day, and I saw this quote: "Significant minority functions have an error case that is expected to never occur." So you get to a branch in your function where you're expecting some input property, and it's not satisfied by this branch. So you say impossible or panic. The impossible has happened, right? I'd like to eliminate some of those. And using more precise types, if you use a function like precisellab, then downstream you can case on bexpr instead of axpr, and so you don't have to provide an impossible case for the lets. So it's a little more robust. There's actually a file in GHC source where they do a lot of this, and Andy Gill, my co-author, says this is pretty prevalent in GHC actually. There's sort of a coding convention that kind of keeps things on the simple side. So they do these sort of, they create synonyms for what's sort of documented as a subset. So CP triv is some subset of the actual core expressions, and those others are related subsets. Some of those restrictions on the subsets could be codified with a new data type. So the question is sort of why didn't they do that? I guess I haven't really just emailed them and asked, but presumably it's because there's this associated cost using precise types. And my notion is that H-Compost mitigates some of those sort of software engineering costs. Because without precise types, previously without H-Compost, if you use precise types, then you couldn't use conveniences like Compost. So hopefully this is lowering the cost of using these precise types in real code. So in the paper, I give this example. And I'm just going to go on a really high level here, because of time considerations. So this is the core of a lambda lifter, which goes from a De Bruijn indexed untyped lambda calculus title type, which you'll see here, to a related type, but it's sort of more precise with respect to the fact that the SC type guarantees there's no lambdas left. Right? You'd like lambdas to be gone after you do lambda lifting. So the general signature is from untyped lambda calculus to sort of a super combinator term. And then the generated top-level functions are sort of in the writer output of the monad. And this is sort of a cutesy benefit of the fields types, is that the type of the two special cases for variables and lambdas almost sort of say what they need to do. Right? It tells you, the type tells you what constructor you're working with. But with this definition, we could add, again, something like product, something that doesn't involve lambdas, something that's sort of agnostic with respect to lambda lifting, and this definition in the paper would continue to work. But the idea here, again, that SC is a more precise type than ULC. But I sort of invented that example from past work that I've been doing. So I looked for a lambda lifter from the literature and found this one from Peyton, Jones, and Lester in 91. And they define a lambda lifter in 3 pieces. And within this paper, they actually do a lot of discussion of where their data types came from and why they chose to use which data types they chose to use. In particular, they ended up using 2. They used an expression data type and a data type for annotated expressions, which I have down here. So in this top box, these are their data types. These 2 are just a slight mutual recursion, so I consider them sort of one data type. They realized that there's sort of an isomorphism between expr and anexpr with like a unit annotation, but they said, well, that'd be troublesome and confusing to have these units everywhere, so they decided to keep 2 data types. Okay? But within that paper, they also discussed these 2 data types. This is exprs where only lambdas are annotated, and this is exprs with no lambdas, right? So this is, again, that sort of super combinator calculus. And they, in a paper, chose to not use these, and they explain themselves of not using them with this. They said, well, they'd just be yet another variant of expr. So again, there's this sort of distaste for variants of data types. And I'm interested in why they don't want that, but I think the major cost of it is, again, not being able to use things like Compost. So I've rewritten their lambda lifter to use precise types, in particular the precise types that they suggested. And so we get a benefit, right? It's sort of the same benefit I showed with the LED elaboration, but in sort of more real-world context. And it's a lot of code, I know, but actually I probably don't have time to go through the details here. We'll just point out sort of, this is their definition, and this is a definition using Compost. So for example, up here, each case basically does 2 things. It converts between the E version of the constructor and the A version of the constructor, so the annotated versus the non-annotated. And then it also computes the free variables of this node given the free variables of the subnodes. But it's sort of doing it all at once. And with Compost, we can sort of neatly break it into 2 different pieces. First, we make the change from A to E, which is trivial. Trivial with Compost, and then we can sort of have a little algebra that builds the free variables of a term based on the free variables of the subterms. So we can sort of restructure the code nicely with Compost providing some generics. And then IG crush is just sort of a fold based on normal instant generics. The second piece was abstraction, and this is sort of a more dramatic simplification. Most of the pieces of abstract just drop the old annotation and convert from A to E. And again, Compost handles the part of that prevented them from abstracting over it in the first place. So Compost makes it a much more concise definition. But it's basically the same shape again. So that's a case where the code actually got simpler, right? And this is a case where the code's pretty much the same, but we have more precise types than we had before. So you get modularity and precision. How am I doing right now? Oh, okay. So I tried to go fast, maybe too fast. I'll slow down. Okay, so in the paper and with respect to this crowd, I think of Compost as a sort of generalization of Compost. So like I discussed earlier, Compost is alpha to alpha. You tell it what to do in the subterms, and it'll give you back a function that just does that to the subterms of the value you give it. Compost is a little more delicate, and it comes down to providing the overrides, right? So the general shape of a function that's defined via Compost is, in this argument, the user handles the constructors that it doesn't want to delegate to Compost, and then Compost fills in the rest. That's the same purpose of this argument here. This is, again, what to do on the recursive occurrences within your data type. But because of the type system, particularly with Compost, it at the compile time, it looks through the constructors in a given data type and tries to find matching constructors in the range. But sometimes, even if I handle lets, for instance, if I don't make it clear to the type system that I've handled lets, I'm not asking you to, not asking Compost to handle lets, then it'll give a type error. So this is where that fields type comes into play. So I'm going to jump ahead, past instant generics. Hopefully most of the crowd is familiar with that. So I needed to extend instant generics in order to provide a generic definition of Compost. These are the two concepts that I added to instant generics. I'm only going to talk about the first one. So I tried to sort of overview it in that last slide with Compost and Compost, but here's an example based just on instant generics, where it shows a benefit of constructor subsets, independent of Compost. But this is also sort of a simpler version of the exact same problem that comes about when you're trying to use Compost and how constructor subsets solve that problem. So in this hypothetical example, we're trying to serialize the data type T. We have this generic serializer that's defined in terms of instant generics. And T has a bunch of constructors here, all of which are easy to serialize using the instant generics approach. But we also have this constructor C, and its second field's a function. And if you try to serialize that using the instant generics approach, it'll object with the type system. But we'll get a type error saying, I don't know how to serialize functions. But in this example, let's say that the second field of C is determined by the first field. With ints, it's probably pretty simple, but it could be a legitimate optimization to cache the computation of this function based on the first argument. But as a clever programmer, we know that we only need to serialize the first argument because we can recover the second argument when we deserialize by just computing the function again. So this, as I said, will give you a type error. So we can use that thought I just explained. So let's handle the C ourselves and then use the generic serialization for the rest of the constructors. So this will still give you a type error. And the problem is that X still has the full type T. So when you apply the generic serializer to X, you're still going to basically tell the type system, I need to be able to serialize functions, and it'll again object. So constructor subsets sort of come to the rescue here. And again, we're using this precise case combinator and the C_fields type. But this goes through. Right? If we could run this code at runtime, it would work. It is well guarded, but the type system can't see that. So the type system is sort of getting in the way. And fields types, which let us talk about anonymous subsets of constructors. In this case, I just want to talk about the subset of constructors in T that is just the singleton set C. So I handle that subset myself, but then X becomes the complement of that subset. It's all the constructors of T that aren't C. And then the generic serializer works for that subset. So this is the point of constructor subsets. And the same exact problem comes up with Compost. In particular, I need to handle the constructors that are no longer present in the range. Okay, so I'm going to skip over the details. Of course, in the paper. I will point out that the fields types sort of complicate the interface. Instant generics is nice. There's just this class that, the type class that captured the isomorphism between a type and its structure. But with fields types, there's sort of this intermediate step. Instead of going all the way from a data type to its complete structure in terms of sums and products, we stop in the middle. We just handle the sum. We leave the products as fields types, which feel like the original constructor. They're in one-to-one, but we haven't represented them in terms of structure, product structure. So this is how we expose a nice interface to the user by stopping at this intermediate stage. But it makes the interface a little more complicated. It's a little more machinery, but the notions are just as simple. This breaks a data type into its sum of fields types. A codomain of a fields type is just the original type that it came from. This is one part of the isomorphism. This is the other part of the isomorphism. The definitions are sort of as obvious as they are in instant generics. It's just a little more machinery. Okay, so I'm going to skip over all that stuff. The interesting part is the related work. sort of asking for help with related work. So constructor subsets, I think, are independently useful, but I haven't found too much that corresponds to them, at least in sort of a Hindley-Miller sort of literature. I think there might be a sweet spot in the design space for constructor subsets from the Hindley-Miller perspective. The things I have found that seem a little related, but also seem a little too general, a little more powerful than we want. For instance, if you use these sorts of things, you might lose some of the benefits of type inference. Or they require subtyping, which is sort of not the part of the Haskell approach. So it'd be interesting. I'm wondering if there's anything else. I think that the other libraries that are similar to instant generics would be amenable to similar extensions as constructor subsets and type-level reflection of constructor names. So you can get Compost even in the other libraries. And then I'm sort of appealing to precise types and nanopasses as the broader scope motivation for why Compost helps programmers, but I don't know of any other work related to nanopasses. And then the reviewers wondered, how's this relate to approaches based on two-level types? And at the moment, my sort of cheeky response is that's solving a different problem. But future work would be investigating how they could cooperate or how one subsumes the other. My hunch is that this sort of subsume two-level types can subsume what I've done. But again, I think that machine is a little, sometimes more heavyweight than you need for the given problem. So this is a nice little, like the lead elaboration of lambda lifting. There's some nice examples that look pretty good with Compost in the precise case. They look just like they would without it, except they have a more precise type. So it's a nice little sweet spot. And then an overarching concern is, like I said, I don't handle the dependent types. So are dependent types sort of this steamroller that's coming through and will just roll right over the usefulness of this work? Or is there a way to integrate and support them? That's all. Thank you.
The discussion for this paper will be led by Patrick Johnson.
Okay. So I guess I can use this place. But so it's really impressive work. I've read the paper and realized that things move fast in the generic programming world. So the first is this instant generics and then extension of that, and then you use that and then work on it. So to really appreciate all the details of what's been done here, one really needs to read numbers of the papers and look at the code. Of course, I should also try to find something to criticize here. So one thing is this software engineering referral in the beginning that sort of sound software engineering practices to reusable things and so on. I think it's also sound software engineering principles to not be bleeding edge. And I couldn't install this package. How much have you had problems with wrestling GHC?
What do you mean wrestling GHC?
Well, I'm guessing if I couldn't install it, that there must have been problems here and there in the type system of GHC and then different versions of libraries and so on.
It's laziness, really. It worked a couple of versions ago. I'm not going to dedicate it. Hopefully people won't use it. But yes, it does use like newer features like hack families and such. But and then I didn't show it. But there's a sneaky part where I'm assuming there's decidable hyper quality, which I had to fake using no like Brazil approach. But that should be supported within a couple versions of GHC. I know Richard worked on a patch that hopefully will be available soon. I don't know where you're at. Good on his head. So that should simplify the implementation a little bit. Like I said, it's bleeding edge, but I don't think it's like we need to do language extension to bleeding edge. It's just one or two versions of that. But yeah, it is. It's using a lot of type of machinery.
So, I was wondering, so writing these kinds of passes, even though they are now more readable and more obviously correct, it's always good to be able to test things. So that's one of the kind of things that helper functions that generic programming could be helping. So in fact, the draw here, there's this, you got an X per data type, and then you got some X per prime, which is a subset. constructors and so on. And then you probably got some kind of a semantics here. And then you would like to test that your conversion, so lambda, lifting, or whatever, actually preserves semantics. So the easiest way of implementing that, I presume, is to implement that function and use the same semantics. Can you implement that one?
Yeah. In the example I gave with the level operation, it's much easier to embed the simpler type back into the larger one. In particular, it's sort of one-liners. So if you're just embedding like that, you're just sort of adding back in constructors that you took out.
Because I think that's a very strong point, because writing this by hand is sort of extremely boring. Because we say a dot lam and then e dot, so it's going to say exactly the same thing but an a and an e or something like that everywhere.
So that's precisely what Compost automates.
Because I think so. That's not pointed out, I think, in the paper, but I think that's an important part. If you really want to test these things, you need to have all kinds of conversions. In this non-bus compiler, there are going to be 17 of them. I guess.
Only 17?
Wasn't it 17 weeks or so?
That's the weeks.
Oh, okay.
There's 50 passes.
Okay.
I think only 6 or 7 of them changed the types, but I haven't done that diligence there. I wanted to point out on that diagram, with 2 level types, you could sort of, that arrow on the left, you could factor it into different pieces of expert constructors, and just apply those directly to the same pieces in expert type. So that's sort of a higher reuse. Right? You're directly using the definition of that function on expert, but on the smaller type. So I see that as sort of an expression proposition. But that's an alternate way to do it. If you just want to go the arrow backwards, that's taken care of already. But 2 level types are pretty much sort of a nicer, more component-based, reuse-based way to do it. That's why I like to integrate with it somehow, or at least try to relationship.
And then the last question, which is not to criticize the work, but identify a thing which I think bites very many people who do generic programming as these libraries with lots of complex stuff in GHC is what kind of error messages do you get when you write something which is not quite correct?
Right. So I expounded on a lot of the issues in the paper in my dissertation, and I have a section about this. And the way I phrased it is the signal to noise ratio is bad. The information you need from the type error in order to fix the type error is present in the type error, but it's sort of amongst a lot of noise. So as I've hacked with this type of machinery in the past, in these cases I've sort of added restricting, like adding a parameter to a type class in order to sort of type around a context. So the type error will say, I can instantiate this class at these types. And one of those types will sort of just be a long, it'll become a big name, which is pretty much a sentence trying to explain the state to me. So I see this as sort of it's a general disadvantage of DSLs that use type class mechanisms in Haskell. It's hard to get DSL type errors out of the GHC, right? So I feel like this is a broad scope issue. With respect to the current implementation, yeah, it's bad. Signal to noise. The information's there. You're sort of living and breathing it, and you can use the type error, but otherwise it's sort of intimidating.
I guess everybody.
Yeah. Other questions?
So I noticed you gave a type for each constructor. So what happens if you want to do nested pattern matching? Does that create?
I have no support for that right now.
Okay.
I've targeted it to really focus on sort of adding and subtracting constructors. So any of my case, I'm sort of making the removal of constructors explicit so that the type checker can see it sort of obviously. And nested patterns sort of complicate that. I like to think of it's much more useful to think of a pattern as total and complete. So working on nested patterns requires some, I think, more syntactic abstraction. Right? So I have determined how to support that. But right now, it's just sort of basic patterns, constructor variables.
Somewhere.
This conversion between precise types is, of course, one part of the cost of having precise types. but the other part is having the types themselves, right? So in this GHC case, you'd have to have like 5 different modules with 5 almost the same copy-pasted data types. So I wonder if that would be possible using some JDTs and dependent types to encode all these cases in just one declaration.
Yeah. Well, for example, I never remember the title of this paper, but I think there's you might have good ornamentation. But it was talking about this sort of using a single data type instead of 2 different ones. But it was more from the index data type perspective.
And would your technique be applicable there?
I haven't figured out support for index data types. I've sort of been using the instant generics branch of the generic programming methodology, and so I'm more interested there on your end. I don't think the gaps are, they're not particularly well supported. So that's sort of a bit of a boundary on what it can be used for. I would want to say a couple things about what you observed. You said that you have to have like 4 modules with 4 data types that are pretty much the same. So the necessity of multiple modules is sort of a technical limitation. I'm making the assumption that the constructor's name, they have to match exactly in the current implementation, but that's just sort of for simplicity. You could make that a little more robust. So you could sort of ignore suffixes, right? So you could have at A and at B. So it could all be in the same module.
Sure, but when you, for example, add a new constructor, you typically have to add it in like 5 different places.
So the second part. That could be handled with really lightweight template Haskell. So the Micropast methodology actually has a little interface for defining a data type in terms of another one. They call it extension. And you just say which constructors to add or which constructors to remove. You could do the same thing. It is a little more complexity to manage. So that's another cost of using precise types. But I think it's sort of smaller and easier to solve than generic versions. But yeah, those are all legitimate concerns about complexity of the system.
Can you explain the types of each of precise case?
Yes.
Specifically, how can you add or remove more than one constructor to a data?
Yes. I was sort of cheating here. I used the unauthorized faking it sort of techniques to make it a polyvariatic function.
Okay.
I don't know if that's helping.
Yeah.
Okay. So at the moment, so there are 3 pieces in all the ones I showed. Precise case, the first argument, which is the discriminant for the case. And then it took a special case, and then it had that default branch. Because of the polyvariatic nature, you can just put as many special cases as you want before the default branch. Just keep providing those functions as arguments, and the type class trickery will just build up sort of the function that handles the subset of types you want to handle specially, and then it'll give all the other constructors to the default list. So the simplest answer to your actual question is you just put another argument there. That's another function on a field type.
So you can dot types each of, but that's what this polyvariate
Yeah.
goes into.
So in the paper I dealt with polyvariatic. You just that first argument is built with a few combinators for combining functions over single field types. But recently I just realized I could do it with polyvariates. So.
Question over that.
Okay. Yeah, it's about your creative works. So yeah, the question about the sweet spot about the subset of constructors. And if I remember correctly, actually there was something called refinement types in the context of standard M, which was exactly that. Because the ability to say that one type is just a subset of another type.
So refinement types, do you know who did that one?
So it's beginning of the 90s. I remember talking of that with Frank Payne.
Okay.
Fanning, Rowan Davies.
Yeah, I remember some thinning work, but it looked more like intersection types, if I remember correctly. But
So if you look just at the paper, maybe it's not so clear, but they really use it exactly for this.
okay.
And another comment is maybe okay. I think there's always a misunderstanding of polymorphic variants. I would say it's not that there are less types there. They're completely types there. But there are more, this is the contrary, there are more variables because they just write down the types that you expect. Because if you don't write it, they're not there.
it's good to have the situation that we could go on and on, but I think we have to stop here. So